As you can see, today we're going to talk about differential equations, the introduction to differential equations. And so before we get started, I mean, this, and it's simply as it says, we need to understand what a differential equation is, we need to understand what solutions to differential equations are, and we'll get to where we're actually determining the solution of a differential equation, but that may not be in this lesson. So anyway, let's get started. Some examples of differential equations and a little bit of terminology. Well, simply put, it's called a differential equation because it is an equation that has a derivative as part of the equation. So for example, we could have something that looked like dy dx, the derivative of y with respect to x is equal to x squared minus 3. Now we've actually seen this type of differential equation in the past, and we've solved this type of differential equation. And this is called a first order differential equation. And it's called a first order because the derivative of highest order, that is the only derivative in this equation, is the first derivative. If you have a derivative like a second derivative or a third derivative or a fourth derivative, then it would not be a first order differential equation. All right, second example is y double prime minus y is equal to 0. Now again, this is a differential equation because y double prime is a derivative and it's part of this equation. And in this case, the highest derivative is y double prime, which is a second derivative. And so we call this a second order differential equation. Now don't be misled just because of this example. You can have a differential equation that has both first and second derivatives in it, but if it has both first and second derivatives in it, it's still a second order differential equation. And our third example, just to give a little bit more flavor here, we might have an equation that is x times y prime minus 2y is equal to x cubed e to the x. So here's an equation that has x's and y's and y primes and e to the x and all this business, but because y prime is part of the equation, it's a differential equation, and of course you recognize very quickly that this is a first order differential equation. Now, what we're concerned with before we worry about solving differential equations is what does it mean to be a solution? What does it mean to be a solution to a differential equation? Well, let's just make that note here. Solutions to differential equations. Well, solutions are actually functions. The solution to a differential equation are functions. See, it's the function that causes, when we replace the differential equation, when we replace the pieces of the differential equation, it's the function that causes it to be true. In other words, in these examples above, basically, it would be what y is, and y is normally a function of x. So our answer might be like y is equal to x squared minus 3 is a solution to a differential equation. So as our first example, the question is this: is y equal 4 times e to the negative x power a solution of y double prime minus y equals 0? That's the middle differential equation up there. So as I said, we expect solutions to be functions or equations, if you will. So here's what we need to realize is that if we're wanting to know a solution of this differential equation, what we're really looking for is if we replace the parts of the equation. In other words, if we put the value of y double prime and we put the value of y, see, if we put the value of y double prime and we put the value of y, does it make the equation true? That's what, of course, it means to be a solution. So before we can decide whether y equals 4e to the negative x is a solution, we need to determine what y double prime is, because that's something that we're putting into the equation. So we know, of course, y is 4e to the negative x, or that's the proposed solution. To figure out what y double prime is, of course, first we need to find y prime. And of course, the derivative of 4e to the negative x is 4 times e to the negative x times the derivative of negative x, which is negative 1. And so that result is negative 4e to the negative x power. And then, of course, what we're really after is how we're going to replace y double prime in the differential equation. So next we need to find y double prime. And it wouldn't take us very long to figure out that y double prime is negative 4e to the negative x times the derivative of negative x, which is negative 1, of course. And that result is 4e to the negative x. So now the question is, do we have a solution? Okay, that's what we're answering. So what we're going to do is, let me write it in here. Okay, that's what we're going to answer. This is what we're wanting to know, whether we have a solution to this equation. So in the place of y double prime, we put 4e to the negative x. After all, that's what y double prime is right there. And minus y, well, y we know is 4e to the negative x. So we replace y with 4e to the negative x equals 0, and we see very clearly and very quickly that that result is 0 equals 0. So the answer is yes to is y equal 4e to the negative x as a solution. It solves the equation. It solves the differential equation. Now, before we move on, we need to understand that sometimes we have solutions given in different ways. And so here's what I would suggest to you. We're going to be concerned about two types of solutions: a general solution, okay, or a particular solution. And it's called different things in different books. But now, in this particular example, y equal 4e to the negative x is a particular solution. It's very specific. There's not any ambiguities here. That is, we have everything defined and set. Now, it so happens that it really doesn't matter for this differential equation what constant we have as a coefficient of e to the x. That is, any equation that is the form y equals some constant, and in this case our constant was 4, but some constant times e to the negative x. Any equation of that form will be a solution to the differential equation. And so we call that a general solution, because any replacement for the constant c is an additional solution. Let's pause here as I turn the page, and then we'll continue with some more information. Well, as you can see, that I've written down our second example, and once again we are going to determine if a particular function is a solution to a differential equation. So as you see here, the question is the function y equal x squared e to the x a solution to the differential equation x times y prime minus 2y equal x cubed e to the x? Now, we can determine what what we need to do. We need to be careful here. It's what we need to do is replace all the y's and y primes with what we know their value is. And so in this position, of course, we can replace that y with x squared e to the x. We're just doing a substitution to see if it solves the equation. But of course, we're going to have to work a little bit to figure out what y prime is so we can put it into the equation. So we start out with the given that we're trying to decide, and we're given y equal x squared e to the x as a proposed solution. Well, from that proposed solution, we would be, if that is a solution, then we would need to know y prime. And of course, to calculate y prime, we see that we have to use the product rule. So we'd say first function x squared times derivative of the second function. Well, the derivative of e to the x with respect to x is just e to the x. Plus, then we'd say second function times derivative of first function, and of course the derivative of x squared with respect to x is 2x. Now, we'd clean that up, and we'd actually write that as x squared e to the x plus 2x e to the x. That's the way we would write that. Now, we're going to do our substitution. So we want to know whether we have got a solution. And so the way we do that is we substitute into the original equation. Okay? The original differential equation. So our differential equation is xy prime minus 2y equal x cubed e to the x. Now we have a replacement for y prime that we just calculated above. So we have x times our replacement for y prime. And there is y prime right there, isn't it? So we'll have x squared e to the x plus 2x e to the x. Then minus 2 times our y value. Well, of course, y is right here, okay? That's x squared e to the x. So we replace y with x squared e to the x. Now we don't have any y's or y primes on the right side of this equation, so we have nothing that we need to do to replace. Now we simply go through and see what kind of simplification we do. We're just performing a little bit of algebra here. And so we distribute this x times x squared e to the x, of course, is x cubed e to the x. And x times 2x e to the x is 2x squared e to the x. And of course, over here, when we multiply with the 2, we have minus 2x squared e to the x. And of course, our equal sign, x cubed e to the x. And now we notice, of course, right here that these two terms will add to 0. So we're left with only x cubed e to the x on the left side, and we have only x cubed e to the x on the right side. And since those two are equal, then the answer once again is yes, y equal x squared e to the x is a solution to our differential equation. And that's, of course, what we've shown. Now, let's see if I have room on this page to do example 3. Well, let me try to squeeze it in here. Example 3, well, instead of wasting your time, let me pause, I'll write down the problem, and then we'll go from there. Okay, you can see here example 3, problem 3. For the differential equation xy prime minus 3y equals 0, we're told that y equals c times x cubed is the general solution to this equation. So no matter what c is, it will be a solution. Y equal 5x cubed, y equal negative 1/2 x cubed, all of those would be examples of particular solutions. Now we're asked to find the particular solution given the initial condition. I see I spelled that wrong. I'm so embarrassed. I don't have an extra n in there, do I? Given the initial condition that y is equal to 2 when x is equal to negative 3. And sometimes that condition is written this way. When x is negative 3, this is like f of x, or f of x is equal to y. So that is, when we put negative 3 into the function f, we get the y value out. So sometimes this is written y of negative 3 is equal to 2, meaning when x is negative 3, y is equal to 2. So that's another way that condition, that initial condition, can be written. Well, it's really quite simple. I mean, it's really an easy process here. We know that in generally, a solution looks this way. Now, we have one more condition, though. There's more information here. That we know that this is what the solutions look like, so we need to know the c value given the information that y is 2 when x is negative 3. Well, that simply means that we replace y with 2 and we replace x with negative 3, and that statement, okay, has to be a true statement, because that's the condition that has to be satisfied. Well, from this condition, we can easily solve and determine what the value of c is. Here we would end up with 2 over negative 27 is equal to c. So that information tells us what the c, for the particular solution, we know the exact value of c. So our particular solution will be y is equal to the c value, negative 2 over 27, times x cubed. Now, of course, that could be written a little differently. We could write that as y is equal to negative 2x cubed divided by 27. Those are equivalent, of course, and so it just depends on the form that our book or whatever software we're using might be given to us. Now, I think before we leave this page, I want to give a graphical interpretation. And what I mean by that is, let me write that down here. I'm sorry, interpretation. We know that any equation of the form y equals c times x cubed will be a solution. So that really means there's an infinite number of solutions to this, obviously, to particular solutions to this differential equation. Say, for instance, we might let c have a value of 1, that would be a solution, or a value of 2, and that would be a solution, a value of 3, and that would be a solution. I mean, as far as that goes, of course, any positive value, but we could also have a value of 1/2, so, or any other fraction. Or we could have c's that were negative. C could be negative 1, or negative 2, or negative 3, or negative 4, or negative 1/2, or negative 3/5, or negative 121 over 13. I mean, any c value we put in there will have a solution. And so what I'd like to do here is show, if you will, a representation of a whole lot of the solutions. Obviously, there's an infinite number of them, and so I can't graph all of those, but I'd like to show you what those solutions would look like. So let me pause and get that graph up.
Okay, you see the graph, or really it's a set of graphs here. And what I've done is I've chosen different values of c, and you see the different blue graphs, the different blue lines. All of those represent a different positive value of c, and the different green lines are graphs that indicate a negative value of c. And of course, c can take on an infinite number of values, and we just have a very few different values of c indicated here. Now, the problem that we had is that we were told that any function of the form y equals c times x cubed is a solution to the differential equation that we had. Now, we wanted the specific or the particular function that satisfied the equation, that is, that solved the differential equation. But the particular one we had, see, what was that condition? That condition was that when x is -3, y has to be equal to 2. And we found out the specific value then, or the specific function, was y equal -2 over 27 times x cubed. In other words, the c was y equal was -2 over 27. And so what I've shown here was with that red curve, that is the y equal -2 over 27 times x cubed. So out of all of the infinite possible solutions, that is the one that satisfies the conditions that we were given. So we found one specific out of very many, or one particular out of an infinite number of choices. And that's the geometric representation to this. Okay, well let's move on then. Let me get rid of this, and we'll continue with the discussion.
So let's move on now to our next example, or our next problem. And we're faced with the question, is x squared plus y squared equals cy? Remember, c is an arbitrary constant. A solution of the differential equation y prime equal 2xy over x squared minus y squared. This has a few twists and turns in it that we haven't seen before. And of course, if you will, in this particular case, we don't really need to replace y prime and compare it to the right side. All we need to do is, based on the proposed solution, determine what y prime is and I think we can do that in this way. So we need we have to, I'm sorry here, I'm stuttering because I'm getting excited, I guess. We need to use the proposed solution, x squared plus y squared equals cy, to find y prime. And that's the whole idea. What is y prime if our original function is x squared plus y squared equals cy? Now, to find y prime based on that, to find y prime when we have x squared plus y squared equals cy, we have to do that implicitly. That is, we're required here, we've got to find y prime, or we can say find derivative of y with respect to x. That's the same as y prime, isn't it? By using implicit differentiation. Okay? So, to find dy dx, then we would end up taking the derivative of both sides with respect to x, wouldn't we? So we'd take the derivative of x squared plus y squared with respect to x, and that'd have to be equal to the derivative of cy with respect to x. Now, in the case of the left side, of course, the derivative of x squared with respect to x is just 2x. But the derivative of y squared with respect to x, if you recall, is 2 times y times the derivative of y, which is y prime. Now, on the right side, we have the derivative of a constant times y, and of course, that's the same as the constant times the derivative of y. And of course, the derivative of y with respect to x is nothing more than y prime. Now, it may be that you want to go and kind of bone up a bit, if you will, on implicit differentiation. I've gone right through this like you remember it very well, and you may need to work on that a little bit more. But now, the issue ends up being, of course, that we need now to solve, okay, for y prime. That's actually what we're trying to find, isn't it? So we need to solve for y prime. That's the way we did this when we were doing implicit differentiation. So we need to get all the terms that involve y prime on one side and all the terms that don't involve y prime on the other. So we'll subtract 2x from both sides, and we'll just subtract cy prime. So it'll look like 2y, y prime, subtract cy prime that we subtracted on both sides. And of course, when we subtract 2x on both sides, it'll look like is equal to negative 2x. Now that we have terms involving y prime on the left side, y prime is a common factor, so we can factor it out. So we end up with 2y minus c times the factor y prime that we just factored out. And so we can solve for y prime now by dividing out the coefficient 2y minus c. So we'll end up with y prime is equal to negative 2x divided by 2y minus c. Now that doesn't really look like what we've got up above, does it? In fact, doesn't look, you know, our differential equation is y prime equal to xy over x squared minus y squared. So the question is, can we algebraically change the form of the right side? And the first thing I notice, and that's what makes this challenging, the first thing I notice is in our original differential equation, the numerator is 2xy. So we actually have a couple of things happening there in the numerator that we've got. Here we have only negative 2x. So we need a factor of y, and we need to change that to a positive. But now we can't just go off half-cocked and multiply by something. Otherwise, we'd change the value of the fraction. So what we're going to end up doing is we're going to multiply by negative y in the numerator and negative y in the denominator. So we're really just multiplying the original fraction by 1, but what I'm going to do is create the numerator that I know my differential equation looks like. And so as we do that, we end up with a numerator of positive 2xy. That's beginning to look more like our original differential equation. Now, when I multiply the denominator by negative y, I'll actually have negative 2y. Let's just make a note here. I'll have negative 2y squared plus cy. When I multiply 2y by negative y, I get negative 2y squared. When I multiply negative c by negative y, I get plus cy. Now, I think what I'd like to do here is change the order of that. So, because I'd like it to say subtract instead of minus, negative 2y squared that is. So I'm going to write that as cy minus 2y squared. That's the same thing, isn't it? Now, here's something that's important to notice, and this is, again, it's a little bit tricky here. If you look at our proposed solution, say our proposed solution says x squared plus y squared is equal to cy. So if that is in fact our solution, cy is the same as x squared plus y squared. Well, down here in what we've been calculating, we've got a cy in the denominator, don't we? So if I replace that denominator, cy, with x squared plus y squared, then our y prime would look this way. Now, as we simplify that denominator, we see that we have a y squared minus 2y squared, which it would end up being simply negative y squared, wouldn't it? So we end up with y prime is equal to 2xy divided by x squared minus y squared. And so here's what we're saying. If x squared plus y squared is equal to cy, then we've determined that y prime is equivalent to 2xy over x squared minus y squared, which means then we have a solution, because that's what y prime is. So once again, we can answer yes, x squared plus y squared equals cy is a solution to this differential equation. Now, in our next 2 or 3 examples, so far all we've really done, I mean, what we've done at this point is we've been given a proposed solution and we've been checking to see whether it is in fact a solution to a differential equation. Obviously, the ultimate goal is to actually find solutions of differential equations. And so we're going to take a few real simple examples, and then from those simple examples, later on we'll expand and do other more complicated things, but that's later in our studies. So let me pause here and set up the first example. Okay, first problem of solving. We're to solve the differential equation dx over dy, derivative of x with respect to y is equal to 2. Now, what we're going to notice, unless we have additional conditions, that is, specific values that we know that the solution has to satisfy, then when we're asked to solve a differential equation, we're getting a general solution rather than a particular solution. And I also want you to note a couple of things here as we will need this as we're working through these problems. The integral of dx, remember, is x plus some arbitrary constant. Anything of that form is a solution, if you will. The derivative of x plus a constant is just 1. And so we're really integrating 1 dx on the left side. Likewise, the integral of dy is y plus some arbitrary constant. So we want to keep that in mind as we solve these differential equations. So this first one that we're looking at, dy over dx, derivative of y with respect to x equal 2. Well, the technique that we'll use here, I mean, this is really a technique. Although derivative of y over with respect to x really isn't a dy over dx really isn't a fraction. It stands for derivative of y with respect to x. We're going to treat it as a fraction. That is, we're going to multiply both sides by dx. So we end up with dy is equal to 2 dx. Now, what we're wanting to know is the function y. And as we said before, if we integrate dy, we'll get y plus some constant. So here's what we're going to do now, is we're going to integrate both sides of this equation. So we have the integral of dy on the left and the integral of 2 dx on the right. Okay? Now, the integral of dy we just saw above, and remember that that's nothing more than y plus some arbitrary constant. Now, let's be careful here. I'm going to make a point. On the right side, we'll also end up with an arbitrary constant. So we're going to have 2 separate arbitrary constants. So I'm going to call this one c subscript 1. Now, on the right side, the integral of 2 dx is nothing more than 2x plus the arbitrary constant. Okay? The second arbitrary constant. Now, remember, the solution to a differential equation is a function, is y is equal to, or some implicit relationship. So I want to solve this for y. So I'm going to subtract that c sub 1 on both sides. So I have y is equal to 2x plus c sub 2 minus c sub 1. Now, here's really the next thing, and after a while, and we get some experience here, we're going to shortcut this. But c sub 2 is an arbitrary constant. We don't know which one it is, and c sub 1 is an arbitrary constant, and we don't know which one it is. So, but c sub 2 minus c sub 1 is just some constant, isn't it? So what we're really going to end up doing here is, rather than say c sub 2 minus c sub 1, which is some constant, we'll just say some arbitrary constant, whatever it is. So this ends up being the general solution to the differential equation above, the general solution. And again, that's exactly what we talked about just a moment ago. We're going to expect general solutions. Okay, well, let's go through another example here. Okay. And this time maybe we'll go a little more quickly because we kind of have the idea. So this one is solve the differential equation y prime is equal to x squared minus 3. Now, I did the first one in a particular form, but the secret to that first problem is that we could separate the dy and the dx, and by integrating both sides, we could introduce a y and an x to get a function. So what we'll do here is we'll replace the y prime with dy dx. See, if we're given something that has y prime in it, we'll replace it with dy dx. And so our equation then looks like dy over dx is equal to x squared minus 3. And then as above, what we'll do is we'll multiply on both sides by dx. And then after we do that, we'll integrate both sides. Whoops, the integral of x squared minus 3 with respect to x. Now, of course, the integral of dy is nothing more than y plus a constant. But let's think ahead. Okay, we're going to have a constant on the left side, like above we call c sub 1. And when we integrate the right side, we're going to have a constant there. But when we solve for y, we're going to get rid of the constant on the left, and we're going to combine it with the constant on the right. So why don't we just write one constant at the end rather than going through that process that we just went through? So over here on the right side, when we integrate x squared with respect to x, we get 1/3 x cubed. Minus, when we integrate 3 with respect to x, of course, we get 3x. And the arbitrary constant we get with this integral is being combined with the arbitrary constant we got on the left side, and we'll just say we have one single arbitrary constant. So this is the general solution of the differential equation from above. Well, you can see this is just kind of a disguised form of something that we've done before, really, isn't it? And what we're working on now are very simple differential equations. We'll expand this, like I said, to more difficult ones a little later. Okay, let's do one more solution, one more problem where we're solving. Let me pause here and get that set up. Okay. We're asked to solve the differential equation y prime is equal to x divided by 1 plus x squared. So as we go through to do this solution or to solve this equation, as before, we're going to replace y prime as a tool with the derivative of y with respect to x in this form. Okay, so we just do that simple replacement. And then we're going to multiply both sides by dx as we did before. So we'll have dy is equal to x over 1 plus x squared dx. Then we integrate on both sides. Okay, integral of dy is equal to the integral of x over 1 plus x squared dx. Now, the integral of dy is y plus an arbitrary constant. But just as we talked about last time, the constant on the left side and the constant that we get on integrating the right side are going to be combined together just on the right side. And so we'll wait to put c on the right side at the end. So we end up with y on the left side, and then, of course, this integral that we've got to work on to decide what this is going to look like. So this is a little more troublesome than what we've had before, and since this is early in this class, let me tell you that we're going to use substitution. That is, we're going to let u equal 1 plus x squared. And when we do, then we remember the substitution method. We'd have du is equal to 2x dx, wouldn't we? Okay? Okay, if u is equal to 2x dx, then we need to actually, here's what we're doing. We're trying to integrate x over 1 plus x squared dx. And when we do this substitution, that becomes the integral of x over u dx. Or we could write that as the integral of 1 over u x dx. But we've got to do the substitution. We need to certainly replace all of the x's. And so from above, up here, we see what 2x dx is. And so we could, from there, decide x dx is 1/2 of du. So this ends up being the integral of 1 over u and times 1/2 du. Now, that 1/2 is a constant factor, so we could factor it outside the integration, okay? And so we end up with the 1/2 the integral of 1 over du, 1 over u du. And of course, the integral of 1 over u is the natural log of the absolute value of u. And of course, now we're going to write in that constant that we're going to need here in a few moments. But u is 1 plus x squared. So this ends up being 1/2 times the natural log of 1 plus x squared plus a constant integration. So now we're basically what we've decided is what the right side is. And so the right side, after we do this integration, is 1/2 times the natural log of 1 plus x squared plus this constant integration, which is the combination of the two constants that we got on each side. Now, this will happen to you, maybe you decided real quickly the situation here, but this will happen is as we're doing this integral, we knew that we had to have an absolute value. But all of a sudden, the answer appears without an absolute value. And why would that be the case? Well, in this particular instance, and we have to be aware of this, 1 plus x squared is always going to be positive. I mean, if x is 0, 1 plus x squared is 1. If x is any positive or negative number, when we square it, we'll get a positive result, so we'll have 1 plus a positive number, which is always bigger than 1. So 1 plus x squared is going to be positive, so the absolute value of it's just the same value. That's the reason we don't need to show the absolute value in the answer. It makes the answer look worse, and it doesn't really add anything to the answer. So that's what we would see here. I think before we leave this, I would like to, and that is the answer, I would like to approach this integral a little bit differently, just in general, because I think this is something that we'll aspire to try to do. Now, a moment ago, we made the substitution that u was going to be 1 plus x squared, and we decided du then was going to be 2x dx. So here's where we are then. Okay, this integral ends up looking like x over u dx. But to introduce the du that we need to integrate with, we need a 2x dx. Now, earlier we kind of solved. We divided on both sides by 2, if you will. But what I'd like to do is generate the expression that I need. That's what I like is a 2x in that place. And then I'd have a 2x dx, and I can replace that with du. But if I have a 2x in that place, if I introduce a factor of 2 in the numerator there, I need to offset that, if you will, with a 1/2 on the outside of the integral. Because remember, these constant factors, we can move in and out of that integral, and 1/2 times the 2x that's on top is the same as x. So I haven't really changed anything. Now, that allows me to replace 2x dx that's on the inside, of course, with just a du. And now we're back in that same position. We just went about it a little bit differently, got the same result, but we just went about it a little differently. And what we see here is probably what you'll see me do if I'm doing problems like this in class. Okay, well, that ends our introduction to differential equations. I hope it's helpful. Good luck on all of your homework.